we are studying the problem, which is called the Dirichlet problem. So the problem is the following. Given domain omega in Rn, it is a bounded domain with reasonable boundaries. Say boundary is smooth or piecewise smooth, so it can be, say, a rectangle. Yes, but I don't consider pathological domains. And we are solving the following problem. Laplacian u equals f in omega, and u on the boundary equals g, where g is given, say, continuous function on the boundary of omega. No, sometimes it's useful to subordinate g to some more restrictive conditions. I will do it later. So this is the full non-homogeneous Dirichlet problem. Now we can a little bit split this problem in two problems. So let us write u equals v plus w. So what is v? V is a function such that delta v equals f in omega. Yes? So we solve the equation. But v can behave differently on the boundary. It can be not g. And so w satisfies Laplacian w equals Laplacian u minus Laplacian v equals 0, because both Laplacian u, equals f minus f equals 0 in omega. So this is one thing. But v can have w can have different values. So w on the boundary equals g minus v on the boundary. Yeah. Now let us denote it by say h of y. So the first problem is, I would say, I would not say that it is easy, but it can be solved immediately in the following sense. Consider a function f in omega. Now it is defined inside omega. So f, say, c of omega bar. And we can continue this function outside omega. Yeah? So f tilde equal f on omega bar, yeah? So this is, say, omega. Here we have this function f, yeah? And now we continue this function and make it a function with compact support. So here it is f, yes, and all in all it is f tilde. So f tilde C of Rn. This means that it's a function with compact support, which is 0 outside some compact domain, say outside of some ball. Yeah? And then we solve the equation. We solve the equation Laplacian W equals f theta in the whole Rn. Yeah? Where f theta is a function with compact support. Yeah? So we how to solve this problem? We want to find a solution of this problem. We know solution. We introduced the function phi of x equal phi depending on module x. It is fundamental solution. It satisfies the following properties. Phi, Laplacian phi is 0 outside 0. So it is harmonic everywhere but at one point. Yes? And if you say modify this function, phi delta equals phi delta convolution with phi. It is modification. Yeah. Then you have that as I explained, Laplacian of phi delta is phi delta. Yeah. So it is a function. Let me draw this function. This function phi is this function. It is singular function. It is singularity at 0. It is phi of x. The function. One moment. I think I have a colored chalk. Yes, I have it. The function phi delta is the same function, but here it is smooth. Phi delta of x. Yeah?
So f is equal to f tilde inside of omega, right?
Yeah.
But isn't the Laplacian of w equals 0 inside of omega?
No, Laplacian W is this f tilde.
But
Yes.
we said
So the first continue this right hand side f. Yes. Then we solve this equation. Where it is?
because earlier we said it's 0 inside of omega.
Laplacian W is f tilde in the whole space.
But isn't f tilde equal to f inside the space?
Excuse me? It is equal f without tilde inside omega.
But inside omega, the Laplacian of w is equal to 0.
To f. Just a minute.
So
It is v. I'm sorry.
v, right? Okay.
I'm sorry. Yes. And So if you take this modified function, then its Laplacian is phi delta. So it is a function such that it is concentrated in a delta neighborhood of 0, and its integral is 1. Yes? And so if delta goes to 0, then you have delta phi equals delta of x. Here is a little overuse of delta, capital and small. No, I don't know what to do with this. Yeah. So the fundamental solution is such a function that its Laplacian is delta of x. So it is harmonic outside 0 and has concentrated, say, Laplacian at one point. And then, so let me recall you that phi of x equals 1/2 module x if n equals 1, 1/2 pi logarithm module x n equal 2, 1/4 pi times 1 minus 1/module x n equal 3, and so on. It is some constant 1/n minus 2 alpha n minus 1 divided by module x to the power n minus 2 for n more equal than 3. Yeah, where alpha n is the volume of the ball of unit. Volume of the ball of unit radius in the n-dimensional space. So this is this fundamental solution, and then we write solution of this equation. Laplacian v equals f. V equals phi convolved with f tilde, or v of x equals integral phi of y minus x f tilde of y dy. This is the convolution. No, if you can accept this as a solution of this equation, yes, I don't say that it is easy to actually find this integral for any non-trivial case. Then we are done with the first problem, and so we have the what is called the Dirichlet problem proper is the following problem: Laplacian W equals 0 in omega, and W on the boundary equals given function h. So this is the Dirichlet problem. Everything is reduced to this problem. Not only the non-homogeneous Laplace equation, which is also called Poisson equation, but similarly the problem of conformal mapping is reduced to a problem of this sort. and many other problems in analysis. So we are studying this problem. Now we introduced the Green's function. Green's function. So again, we have domain omega. We take a point x, and here we have a point y. So x and y are points of domain omega, and Green's function is the following function g of x, y, such that first Laplacian g, Laplacian with respect to y, g of x, y, because it's function of two variables, we have to write with respect to which, equals delta of x minus y. This means that g of x, y equals phi of x minus y. This function has singularity when y equal to x. Yeah? Plus some harmonic function, say c of y, such that Laplacian c is 0 in omega. Yeah? But it is not enough. So we have to this g of x, y.
Yes, sir. It is plus or minus.
Excuse me?
There is plus or minus. Before in the previous lecture you write minus.
You mean before the psi y?
Yeah, yeah.
It was Laplacian with respect to x.
No, I mean phi x minus y minus or y.
It's the same, because if phi is, if psi is, you mean here minus phi?
No, minus.
Minus psi?
Yeah, yeah, yeah.
Okay, let it be minus psi. But minus psi is harmonic if and only if psi is harmonic. So it is some, I would say, correcting function, correction, and important thing is that second condition, g of x, y equal 0 if y in boundary of omega. So gxy is a solution, if we fix x, it is solution of the following boundary condition. That it's for fixed x, it is a function such that its Laplacian is delta function at a given point x, yeah? And it is 0 on the boundary. Now, you see that instead of this, you can consider the problem for the function psi of y. It should be harmonic, and its values on the boundary should be equal to the values of phi on the boundary. Yeah? So it is a case of this problem. So these two, I would say, difficulties can be pumped from one to other. Either we should solve non-homogeneous problem with zero boundary conditions, or you have to solve homogeneous problems or for the pure Laplacian equation with some non-homogeneous boundary conditions. Yes, because if both are zero, the Laplacian is zero, and on the boundary it is zero, the function can be only zero. No, we have proved it using the maximum principle. So if the Laplacian is zero, then the maximum is achieved on the boundary, minimum is achieved on the boundary, and on the boundary the function is zero. So both maximum and minimum are zero. Yeah. So the thing that we have to find the Green's function. Now another thing is that if you look at the possible solution of this problem, solution Laplacian W is 0 in omega, W is H on d omega, so it is our solution. W of y. Of function y. Yeah. Then we can write the following identity. I wanted to transfer to other beast, which is called Poisson kernel or Poisson function, which is even more important than the Green's function. So integral over omega W of y Laplacian g of xy dy equals integral, if you integrate it by parts, over d omega W y d g of x y d nu y ds. Yeah. So if I did not mistaken, and what is mean? It means Laplacian of g of xy is delta function of the point x. So integral delta w of y, delta of x minus y dy equals now w of y on the boundary is h. Integral it is over omega. Integral over d omega. H of y dg of xy d nu y ds. And now what is this? Delta function or integral of function of y times delta function of x minus y. So this function is concentrated at the point x, and it has unit integral. So this means that the following. W of x equals what is written here, integral h of y d omega h of y dg of xy d nu y ds. And for this function, normal derivative of Green's function, we can introduce special notation. Integral over d omega h of y k xy ds, no, it relates to y. So k of xy equals dg of xy d nu y, where y is a point on the boundary. No, if we want to write this formula, we should have at least that the normal vector to the boundary exists at the point y. Yeah? So the boundary should be differentiable to have a normal vector. And we can a little bit say weaken this solution, this condition, say that the boundary is piecewise differentiable. So, for example, a rectangle is a good domain, yeah? But a domain whose boundary is very hairy, so it has no tangent at every point, this simple meaning is lost, so we have to use more sophisticated notions, which I am not going to do here. So this W has the property Laplacian W equal 0 in omega, and W on the boundary equals h of y. So W is a solution of the homogeneous Dirichlet problem. So Laplacian is 0, so Dirichlet problem for harmonic function satisfying this boundary condition h of y. So we have solution provided that we have this Poisson kernel. And we have this Poisson kernel if you have a Green's function. And we have a Green's function, after all, if you are able to solve the Dirichlet problem. Yeah? So you see here a circle. Yeah? And we created a set of definitions which very well match one another, but they are circular. Yeah? So it does not help us to solve the problem. And as a result, we have very few domains where we can find the Green's function and the Poisson kernel. Yeah. So very few domains. One of this domain was just half space. Yeah. In the half space, let me now do it. What I'm doing now, I just repeat what was before. Rn plus it is the half space. No, for any half space, so we have a plane. It divides the space in two parts. Then you introduce the coordinate system such that in this coordinate system, this domain half space is described like this. And then we use the reflection idea. We write the function phi, let me write g of x, y equals, let me write phi of x minus y minus phi of x bar minus y. So what is x bar? X is x1, x prime, xn, and x bar is x prime minus xn. So this is the point x, and this is the reflected point x bar. Like in the complex numbers, conjugate number, yeah? And now let us see that first of all, this second part as a function of y is harmonic everywhere in the upper half space, because this function it's harmonic outside the point x bar, and x bar is in the lower half space. Yes, please.
Sorry, last time we defined the green function like phi x minus y minus phi x is the same.
X bar minus y. One moment. No, this way. In fact, Green's function is symmetric. Yes, g of xy equals g of yx. Yes, so it is, in fact, it is the same. Yes, but, okay, let us do it this way. Yeah, so as a function of y, this function, this is harmonic in the whole upper half space. This is harmonic outside the point x. At the point x, it has singularity such that its Laplacian is delta function at the point x. So, and most important is that when y is on the 0, so if y equals y prime yn, yn is 0, then modulo x minus y equals modulo x bar minus y. Yes? So if y is here, then these distances are equal. And so this means that this function, okay, g of x, y is 0 on the d r n plus, which is y prime y n, such that y n is 0. So this way we constructed Green's function on the boundary. And we construct Green's function inside the upper half space. We have this Green's function, and having this Green's function, and we have the explicit formula for Green's function, we can find the Poisson kernel. No, k x y equals d g d x n with d mu y. So what is the normal vector? Normal vector is this. It is unit vector looking down. So its end coordinate is minus y. So it is minus dg of xy dyn. Yn equals 0. At this point, you can see that the derivative of this and derivative of these parts are equal. Yeah? And so it is tau times minus d phi x prime minus y prime xn minus yn dyn. Yn equals 0. Now let us substitute. What is this? Phi of xy of xy equals x minus y. Phi of model x minus y equals 1 n minus 2 alpha n model x minus y to the power 2 minus n. Now let's differentiate it. No, you know what? I work in this n more equal than 3. For n equal to it is logarithm, but for logarithm you have already done. So now I'm going in the more general case. Phi x minus y equals the same 1 n minus 2 alpha n times sum x k minus y k square k from 1 to n all to the power 2 minus n equals 1 n alpha n because 2 minus n kills minus times 1 moment 2 minus n divided by 2, of course. So it is 2 no 1 divided by 2. Now sum xk minus yk square 2 minus n divided by 2, it is minus n divided by 2 times x dyn of this equals d dyn equals d dy. Yes, now I differentiated already. Times x minus y 2 x n because yn is 0.
Yes, sir. Do you need to put minus before?
Excuse me?
Do you need to put minus? But the formula for 3 dimensions is minus 1 over.
No, I find the derivative and then I insert this. Yeah, minus 1 equals minus 1 n alpha n x minus y to the power minus n times xn. And k is dg du. It is simply twice with minus. K xy equals minus 2 d phi x minus y dyn yn equals 0 equals 2 n alpha n x n x minus y to the power n. Oh. So this is the Poisson curve. And now I want to say that this kernel has the following how can you visualize it? It is, first of all, This is the point y. Yes, this is the point x. Y is on the boundary, x is here. So as a function of x minus y, if y is such as yn is 0, you see it is homogeneous of order 1 minus n. K x minus y is homogeneous of order 1 minus n. First of all, so along each this ray, it decreases as the distance to the y to the power 1 minus n. It is just 1 less than the function phi itself. First thing. Second thing, let us consider this function on the line xn equals epsilon. Yeah? On the plane xn equals epsilon, y epsilon for epsilon is something which is small. We have k of xy equals 2 n alpha n, and here you have epsilon divided by x minus y to the power n. Let me write it in the following form. X prime minus y prime square plus epsilon square to the power n over 2. And now let us look what we have. So it is a function, after all, if x prime is fixed, y prime. Yeah? X prime minus y prime. Or let me write y prime. And here is x prime. When x equals x prime is y prime, this is 0. And all in all, it is 1 over epsilon to the epsilon here to the power n, 1 minus n. Epsilon to the power 1 minus n. So when n is more than 2, it is no considerable thing. It is high. And then when x prime minus y prime grows, it goes to 0 fast enough. Yeah? So when it becomes macroscopic of order 1, then all it becomes of order epsilon. Yeah? And then because it is for x prime minus y prime much more than epsilon square, than epsilon, this dominates, so the denominator goes to infinity as this difference to the power n. So you have all in all this picture. It goes to 0. Yeah. So when it becomes of order 1. It becomes of order 1, then it is of order epsilon, so it is x prime minus y prime to the power n should be of order epsilon. So it is epsilon to the power 1 over n. And the integral kxy dy prime integral it is 1. So if you integrate it along this plane xn equal epsilon, for any epsilon, it is 1. This integral. No, just look yourself and you will see it. What I wanted to say, that this is a delta-like function. When epsilon goes to 0, its domain where this function is considerable shrinks, like epsilon to the power 1 over f. And its height grows like epsilon to the power 1 minus n. And all in all, the integral remains 1. So this means that the following thing, that let me write it. K x prime x n y prime 0 0 it is always so y prime goes to delta of x prime minus y prime as xn goes to 0. So this Poisson kernel plays the same role as the fundamental solution. Fundamental solution transforms a function in the space into the function in the whole space. Yes, just convolution with fundamental solution. And here we do convolution with the boundary function. And it transforms the function from the boundary to the function in the whole space. Yeah. So I would say, what is k x y? K x prime x n y prime is the solution of the following problem. Delta W with respect to x of x equals 0 in domain R and plus. W of x at the point on the boundary x in D R n plus equal delta function at the point y prime. So if you put a delta function in the boundary condition, yeah, just imagine that this boundary function has a very high bump or spike, yes, so that total integral is 1, but it is concentrated on a very small domain, yes. Then the result, the solution of this boundary problem is given by the Poisson kernel. Yeah? Yes, please.
Are we taking the Laplacian in respect to x boundary derivative of y?
It is the same. It is a little. K xy equals k of yx, as we proved. Yeah.
I know we did the
Not k, g.
G, yeah, G.
But this function, if you take the definition, the formula for this function, k, it is the normal derivative of the function of x as y's parameter when y is approaching the boundary and derivative with respect to y. Yeah. So, and if you have a family of harmonic functions depending on parameter, then derivative of this function with respect to parameter is also harmonic. It is linear derivation. Because the sum on difference of harmonic function is harmonic. Yes, if you divide by dy, it is also remains harmonic. So we have it. So this means we solve this, so to say, elementary boundary value problem, elementary, elementary Dirichlet problem, and then we say construct a solution for general Dirichlet problem as linear combination of these elementary solutions. This solution depends on parameter y prime on the boundary. Yeah. So for different y, we have different boundary value of function. So multiply by boundary value, then integrate with respect to y prime, and we have the whole picture. Yeah. By the way, here it is. Let me write it again. K xy equals to n alpha n xn x minus y to the power n. Now, in particular, when n equal, it is n more equal than 3. And for n equal 2, we have 2 divided by n equal to alpha n. It is the radius of it is the volume of the ball. It is 4 third. No. The volume of the ball is p r square, so it is the volume is the area of the disc is pi. X2 x minus y square. It is also correct. We got exactly this formula, so it is 1 over pi. We got this formula from the logarithm, because in two-dimensional the fundamental solution is logarithm. Yes. So this way we reached our initial point of today's lecture, I wanted to say. So all this was before, no, save the last thing we did for n equal 2, and now we did for a n. And now let me make, in the last 10 minutes, one small step forward. So I want to consider Green's function in the rectangle. How to construct it? So it is x1, x2, or better to say y1 and y2. Because x will be a fixed singularity and y is the second parameter, the second variable, and we have a rectangle with sides, say, m and n. And here we have the point x, x1, x2. No, if y1 and y2, let it be L1 and L2. We know how to construct in the Green's function in the half plane using reflection. Now we use here the same idea, but this time we have not just the sum of two terms, but infinite series. So let me divide all the plane into rectangles, which are rectangles, shifts of this rectangle, original rectangle. Let me draw it in red. So shifts by L1 in the horizontal and L2 in the, no, I would say n times L1 here, m times L2 here, m and n are correspondingly all integers. So let us take the second point, let it be red. Let us take the second point at x1, x2, and it is x1. So we have to add a1, plus this a minus
2L1 minus x1.
2x1 minus L1. Yeah? x2. So this is the point such that its distance from this vertical line is the same as here. And here we put the function phi. No, okay. Let me write here sign plus, here sign minus. Now let us reflect in this direction, this point. X1 2 x2 minus L2. It is this point. So this point is obtained from this by reflection. And put here also the sign minus. Minus here is white. And so on. In the rectangle, let me enumerate this rectangle. R0 y1 less or equal than L1.
Sorry, are you sure?
Y2 less or equal than L2. Excuse me?
If x1 is really small, it doesn't make sense to have 2. I think it's 2L1 minus x1.
Yeah, actually, it's bad.
No.
I think x1 goes to 0.
Yes. L1 minus x1. 2 L2 minus x2. Yes. And R0 0. R PQ. P L1 less than y less than P plus 1 L1, Q L1 less y1 y2 less than Q plus 1 L2. So each rectangle here has two indices, P and Q. And in each rectangle, we put a point x1 PQ equals, let me write here, L1 over 2 plus P L1 plus minus 1 to the power P x1 minus 1 to the power P, just a minute, it is in this direction, x1 minus L1 over 2. So this means that in the odd places we move it to the left from the center. No, if it was from the to the right. In the even places to the right. And correspondingly, it is x2 PQ equals L2 over 2 plus Q L2 plus minus 1 to the power Q x2 minus L2 divided by 2. Now let us check. When P is 1, L1 divided by 2 plus L1 minus x1 plus L1 divided by 2. So it is 2L1 minus x1. You are right. Yeah. So in each of these rectangles, we have this point x1 pq, x2 pq. Yeah? And now let us put in each of these points the singularity of the fundamental solution with a sign plus or minus, depending on p and q. So let us write g of xy equals the sum minus 1 to the power p plus q, because any change of p or q by 1 leads to change of sign, times phi of x p q minus y. X pq equals x1 pq, x2 pq. Sum, it is double sum. pq from minus infinity to plus infinity. So in fact it is double sum. Now, what is important? No, formally, we have the following thing, that when we are, say, on the y2 axis, yes, then every y is y1 is 0, for example, then every contribution of every singularity on the right is cancelled by opposite contribution from the left. Yeah, you can see. So here it is with plus, here corresponding point with minus. So they will, they are at equal distance from the axis, so they will cancel one another. And the same for all other pairs. So the same is here on all four sides of the rectangle. So this way, and we cannot make, we cannot do it cheaper. We should consider this infinite, double infinite series. Yeah? So it is not a great trouble. The trouble may be convergence, because this function phi decreases as 1 over x minus y to the power n minus 2. Okay? So this series does not converge absolutely. You can find that in the absolute sense it's not convergent. Yeah? We have to rely on the cancellations. So we have to sum it accurately. No, for example, so P and Q, you say in the, we did it in the say of the plane, so n equal to, so the function phi is a logarithmic function, yeah? So logarithmic function is not even not bounded, yeah? But because here we have different signs, say from here comes logarithm with one sign, from here immediately with other sign. So logarithms, their values cancel one another. But next comes derivatives. Derivative of order 1 over r. Yeah? It also, if you consider in the plane, we have this p, it is q, so consider all the integer points here, yeah? Then you can see that the series for the second derivative, for derivative also diverges. And for the second derivative, it also diverges if you try to do it naively. It is not absolutely convergent. Yeah? So we have to carefully analyze how different terms, say here and here, how they do cancel one another. No, at least main part. Yeah? In fact, it is done. It is correct. Yeah? Similar things are made. No, in fact, the main domain where it is done, it is in complex analysis, where we singularly define, say, elliptic functions as functions which have some sort of singularity at the periodic, doubly periodic system of points. Yeah? Doubly periodic functions. So it is what is called Weierstrass elliptic functions. And here we have, I would say, a real analog of these functions. No, there is a cheaper way to do it using the Fourier method. So we can do it using Fourier method, but we did not touch it, so let us not go. So we can do this way. Yeah. So it is a good opportunity to think yourself if you are interested. You can think how to prove that this series really converges. In which sense it converges? Yeah? No, for example, if you consider the sum of over all the points which are inside of a circle of radius r, how to prove that this sum converges? The sums go to some limit when r goes to infinity. It is a good task because we have to analyze behavior of different derivatives. Yeah? No, if somebody is bold enough to do it, he will have his exam. I mean, that's it. So I abuse my time, so let us see you. Now, because of the virus, I would not like to have office hours. So if you have questions, please write me. You can even organize, if necessary, rendezvous by Skype. Yes, if necessary. But I think we don't need it. Okay, so for now, let's finish.